Hello and welcome to Lesson 6. This lesson is the start of 2 lessons dedicated to examining heat transfer. The baseline assumption I've made in designing these lessons is that you will have come across heat transfer at some point in a previous degree course, and that the material you're about to see will serve as a reminder of the key points as applied to polymer processing. If you haven't come across heat transfer before, then I've tried to include enough detail and sufficient examples to illustrate the key points. I've also proposed a problem-solving workflow for you to follow, such that most problems you'll encounter will be solvable. Before we get into the detail though, let's see why we need to have a good working knowledge of this particular subject. Now, one of the ways to motivate the study of heat transfer is simply to look at an extrusion line. So here on the whiteboard, I've got a schematic diagram of a very simple extrusion line. As you can see, it's been taken from the Netlon example that we saw a few lessons ago. And if we look at what's going on, we've got an extruder, we've got pellets loaded into an extruder, the pellets are being molten, the molten material is being squeezed through a die to form a shape. The shape is then locked in by solidifying the material, and then there's downstream processes that may involve orientation and maybe some stress relaxation. Now, let's think about the thermal history of the material as it goes through this process. So to start with, we are loading solid pellets into an extruder, ostensibly at ambient temperature, and these pellets need to be heated to their melting point, then molten, and then conveyed in the extruder in their molten state. And so we've got a heat transfer problem there to start with, because we need to ensure that enough heat gets from the extrusion line into those pellets such that they then melt and then achieve the desired liquid phase temperature that we're looking for to achieve the rheological characteristics we desire. Now, mostly that's going to be by a mixture of conduction and convection, as the pellets and their subsequent molten phase is sort of mashed around by the extrusion screw. But one of the things we also need to be aware of is a phenomenon we're going to be looking at a lot next lesson, which is that of heating due to internal friction within the liquid. And this is a phenomenon we call viscous dissipation. So already, just looking at part of the extrusion line, we've got a lot of heat transfer processes going on. Let's move on to the extrusion die. Now, maybe, perhaps, the flow in the die is isothermal. Well, if the die has got lots of small detail in it, lots of small flow paths, then there's probably going to be quite a high volumetric flow rate or a high flow velocity in these areas, which infers a high shear rate. And again, we come back to the whole question of internal friction and viscous dissipation. And that can have a significant heating effect on the liquid phase in those high shear rates, which in turn alters their rheology, because we now know that the rheology of polymers is very temperature dependent. And so even though we might design our die to be isothermal, it may well not be as a result of the flow within it. Okay, so we make a product, it comes out of the die, and usually there's an air gap between the die and the means of formal quenching. And so in that air gap, we've already got some natural convection cooling going on. And so has the polymer formed a skin by this point? Have we got an internal core? Or has there been no real change in the state of the polymer other than it's got a little bit cooler? We need some heat transfer knowledge to be able to work that out. Then we've got the quenching process itself. And so the aim of these processes is to solidify the polymer. And so what we're trying to achieve is a thoroughly solid polymer all the way through the extrudate. So at that point, we need to know what the relative rates of heat transfer are internally within the polymer and externally from the polymer to the quench. We don't really want to exit the quench tank with a nicely solidified polymer skin and a nice gooey molten core. And so we also need to be aware here of latent heat releases due to that phase change. So again, there's a lot of heat transfer theory going on within a quench. Now, depending how quickly steps 2 and 3 and 3 and 4 occur, we may find that we might have residual stress locked in our product. And that residual stress is going to be in the solid phase. So that solid, as it comes out of the quench bath, well, hopefully solid, not with a gooey interior as it comes out of the quench bath, is going to cool. But that stress is going to remain there. And so we may need to design in a further heating stage to release that stress. So we might have a stress relaxation step. And a good example here might be, for example, polyester yarns. If there's too much locked in stress in a polyester yarn, the first hot wash it goes in, everything's going to shrink. And so if we step back from what I've just been talking about, we can see that there is a lot of heat transfer going on in even the most simple extrusion process. So therefore we really need to understand in quite some depth how heat transfer processes work. So what I'd like to do now is to introduce to you the main equation that we use to describe heat transfer. And what I really want to get across is that it's quite simple. We can get lost in the complexity of it, but I urge you not to do that. I urge you to try and keep it at a level where actually you can visualize what's going on. And so the level we need to be at to think about that is we're dealing with the most fundamental rule of chemical engineering. In minus out equals accumulation. And the substance that we're talking about in terms of in, out and accumulation is simply energy. We can have energy input, we can have energy removal, and if those are imbalanced, we will have energy accumulation, which may be positive, as in there's an increase in energy, or it may be negative, as there's a decrease in energy. So in minus out equals accumulation is what we need to be thinking about. Now, we can convert this into mathematical form. And when we do that, don't be alarmed. We've just got the same principles going on. Now, I'm going to go through each of these terms in great detail in this part of this lesson. The first thing I want to do is to look at the units that we're measuring things in. Whenever you look at an equation that may be unfamiliar, or for that matter, even one that is familiar, always ensure that you understand the units of measurement. And so if we look at each of these groups of terms, we find that for the energy transport equation, we're dealing with units of watts per meter cubed. It's a volumetric heat transfer equation. And this becomes very important when we manipulate the energy equation and when we flesh out these source terms, these heat flux terms, into physical processes, because we need to make sure that we're always dealing with watts per meter cubed. Otherwise, we're going to get a very wrong answer. Okay, so let's put some nomenclature to this equation. Going from left to right, SH is a source term, a volumetric source term. We're going to go into more details in that in a minute. Q here is a term that involves heat fluxes. So Q is a term that involves heat transfer through area, through surface area. So on the left-hand side, we've got how energy changes on a volumetric basis, and then how energy changes by a transfer means through an area of material. On the right-hand side, we've got something quite interesting. We've got this total derivative, big D by big dt of temperature, pre-multiplied by rho Cp, such that we get watts per meter cubed as our units. And then, of course, we can split big D by big dt apart to give a transient term, the partial change of temperature with respect to time, and also what we term an advective term. This is the amount of energy that's coming into our region of interest as a result of flow. And if we look at that term, v dot grad t, we'll see that v here is a velocity vector, and grad t is a vector of temperature gradients. And we'll go more into detail in this in a little bit. So let's take a quick pause. If anything here looks unfamiliar, specifically vector calculus or manipulating vector quantities, please go and do a little bit of maths revision. There's 2 videos I've linked here on the whiteboard, and the description will be in the notes of these videos. And there's revision material on scalars and vectors from EPD650, and also on basic vector calculus, again from EPD640. So fear not if this is unfamiliar. Go and revise these principles, and then everything will become very familiar again for you. Now what I'd like to do is to go into each of the terms of the energy equation and talk through them in a lot more detail. What we're trying to achieve here is a mental picture of what is going on in any particular heat transfer scenario. So let's start with our volumetric source term. And I'm going to say that SH here is going to be in, is going to be heat generation term if it's positive. And so what I'm going to do in each of these little examples is imagine a cartoon of a heat transfer example. And that cartoon involves a little cubic box. That's what I'm going to call my control volume. That's my region of interest. If something's happening internally within that, on a volumetric basis, like there's, I don't know, a phase change, for example, going on, then we're going to say this is part of the term of SH, my heat source. And so this energy release is on a volumetric basis and can occur through a number of different physical means. There could be a chemical reaction going on. This is happening within the bulk of the material and is therefore a volumetric heat source term, or a volumetric heat requirement if it's negative. So our sign convention here is positive for energy release. Specific to polymerization and polymer processing, we might have a heat of crystallization, either positive or negative, depending whether there's formation or destruction. We could have phase change. We've seen from our extrusion line, things melt. That's a latent heat involved. Things solidify. There's a latent heat involved. We might, have another means of generating heat within a unit volume. Microwave heating, for example, if the right chemical bonding is there to resonate at those microwave frequencies. One of the other volumetric heat sources we're going to see in later parts of the next lesson is internal friction due to flow, viscous dissipation. That is a heat source that comes into this SH term here. So, SH is all about what happens on a volumetric basis within our little control volume. Now, let's move on to another mode of heat transfer, which is not what's happening inside a volume, but it's what crosses the surfaces of that volume. So let's talk about Q. So this can either be an input or an output, depending on the sign of the terms. Notionally, I'm saying it's an output, so my outflow is going to be if my energy terms are positive. And I'm going to break Q apart into the three different physical mechanisms that can contribute to it: conduction, convection, and radiation. So let's think about conduction first. So heat transfer by conduction, we've got terms here that look like they're vectors because they're in non-italic script and bold. And so my conduction heat flux, little qc, has units of watts per meter squared. K, my thermal conductivity, has units of watts per meter per Kelvin. My temperature gradient, grad T, is Kelvin per meter. And so if we multiply watts per meter per Kelvin by Kelvin per meter, we get watts per meter squared. And then if we look in the main equation, we've got the gradient of QC, which gives us our volumetric units that we need for the energy conservation equation. Now, grad T is a vector quantity. It's a change in temperature with respect to each of the three coordinate directions that are in our coordinate system. I've assumed isotropic conduction. That is to say, the thermal conductivity of the material is the same in every coordinate direction. That might not be the case, in which case we have to make K part of that gradient term. So we've got Kx dt dx plus Ky dt dy plus Kz dt dz if K is non-isotropic, if we've got different thermal conductivities in each of our coordinate directions. We're going to keep things simple. We're going to assume that the thermal conductivity is the same in every direction, and there are no gradients in thermal conductivity. So let's have a look at a little cartoon again. Let's build this mental model. The blue thing here is my bulk of material. My control volume sits entirely within that bulk of material. And what I'm going to say is, look, I've got heat transfer away from my control volume if the temperature inside my control volume is hotter than the temperature outside it. And that's positive heat transfer, so therefore it's an outward heat transfer process. Of course, if the temperature inside my little control volume is less, then we get the opposite scenario happening. So if T1 is now colder than T2, we're going to get heat transfer from the surroundings into the control volume. But my sign convention again is that a positive term means it's an outward heat flow. Okay, so that is conduction heat flux. As we can see, heat crosses the faces, the area of that little control volume. It's not being generated internally. It goes into or out of. Now there's lots of other heat transfer processes that go into or out of. So let's look at the next one, which is convective heat transfer. Now heat transfer by convection takes the form I've just put there on the board. We've got a heat transfer coefficient H, measured in watts per meter squared Kelvin. And again, that watts per meter squared Kelvin kind of makes you think it's crossing an area. We've got a temperature difference which drives the heat transfer. And then we've got an area to volume ratio, because we want big Q convection here to still have units of watts per meter squared. And so what we're looking at is the amount of surface area per unit volume that this heat transfers across. Again, let's think of this in a cartoon. So this time in my cartoon, I've, say, got a thin polymer section. My control volume sits all the way around it, and the surfaces of that thin polymer section lie within my little control volume. And so within my little control volume, I have got energy crossing a surface. And so that energy crossing a surface is due to natural convection. And I can see that if my polymer is hotter than the external surroundings, then I have heat transfer away from that polymer across the faces of my little control volume. And so again, that is a positive heat transfer, and that reflects a heat loss. It can, of course, be the other way around. Okay, now in a very similar vein, we can think about radiative heat transfer, because again, radiation heat transfer crosses a surface. So if we think about what big Q subscript rad might look like, it looks a little more complex, and we're going to be talking in a lot more detail about radiation heat transfer in the final parts of this lesson. What we see is that radiation heat transfer, as measured in watts per meter cubed, consists of the Stefan-Boltzmann constant, little sigma, the effective emissivity of the surface and the heat source, and then how much of the radiation, let's say, emitted by the heat source is gathered by the surface. That's captured in script F, my view factor. More about this later on. A to V is my surface area per unit volume again inferring that radiation heat flux needs a boundary to cross. And then we've got my temperature driving force, but note that it is quartic in temperature, and therefore whenever we deal with radiative heat transfer, we're dealing with a mathematically non-linear problem. Again, let's think in a cartoon. It's a very similar cartoon to what we had before. I've got, for example, a thin polymer film. I've got my little control volume sitting all the way around that little polymer film, such that it includes a surface. And let's say I've got a hot polymer and a cold environment, and so my heat loss is going from the polymer to the environment. And again, if we notice the diagram, the heat flux is crossing the surface. Okay, so we've got a heat flux of watts per meter squared going on. Okay, so we also need to think what is going on in the other terms of this equation. We've dealt with all the terms on the left-hand side now, notionally in minus out. We've actually got another kind of heat loss term if we split open that total derivative and look inside it. That V dot grad T term has got a name. It's energy advection. It's energy transfer as a result of the motion of the material. If we think of a molten polymer, it's the motion of the fluid. If we think of a solid polymer, it's how that solid polymer may move through our region of interest, our control volume. And again, it's energy removal if the terms are negative. So let's have a look at V dot grad T in a bit more detail. What we see is that both terms are vectors, and we've got the dot product of two vectors. V is a velocity vector, grad T is a velocity vector. The dot product of a vector with a vector gives a scalar, and that is what we need, because if we look at the energy conservation equation, SH minus Q equals rho Cp dt by dt, it's a scalar equation. We cannot add scalars to vectors. So whenever we've got vectors in there, there needs to be a way to make sure that we end up with a scalar result. And V dot grad T, that dot product, is how it is achieved. In a simple coordinate system, let's expand this out, because we need to be familiar with operating with these vector quantities. V is just a vector of velocities in Cartesian coordinates Vx, Vy, Vz, the motion of the fluid in each of the three coordinate directions. Grad T is simply a temperature gradient. It's dt by dx, or dt by d coordinate dimension. For my Cartesian coordinates, it's dt dx, dt dy, and dt dz. So if I use the dot product between that velocity vector and that temperature gradient vector, I simply get Vx dt dx plus Vy dt dy plus Vz dt dz, as I've written there on the board. And we can see that it is a velocity in a particular direction multiplied by the temperature gradient in that same direction, and then all of those terms added together. Again, let's think about this diagrammatically. There's my polymer film. It's a thin film. It's encapsulated by my little control volume, and the control volume sits all the way around it. And the film is coming in one side of my control volume and leaving the other. And as we can see, if there's other heat loss processes going on, the temperature that comes in is going to be different to the temperature going out. Imagine that we've also got convection going on. But how much energy comes out is going to be dependent on how big those other heat loss processes are. And we'll be talking a lot more about this in future parts of this lesson. And so we can see that an advection process is simply another means of taking into account of whether heat is coming into or being removed from my little control volume. Okay, let's look at the final term. We've done in minus out now, where in could be in or out depending on the sign of the terms, and out could be out or in depending on the sign of the terms. Let's look at the right-hand side, the accumulation term. So again, let's think of this as my little control volume. It might be cold to start with at time t equals 0. Let's say a heat transfer process happens, and over time, my little control volume warms up because there's more energy coming into it than there is leaving it. And so this is simply an accumulation term. And so again, the accumulation term is positive for an energy increase. And of course, this is time dependent. So that is what our energy equation is describing. It's simply in minus out equals accumulation, where there are multiple physical processes for in minus out. And if there are multiple physical processes, we can see that whether it's happening in 1 dimension, 2 dimensions, or 3 dimensions is going to affect the form of the mathematics that we use to solve the problem. And we are going to be striving to get an answer to a problem that is sufficiently fit for purpose. And so we may well be simplifying the problem as far as is reasonable, such that we get an answer that is quick to arrive at and yet still fit for purpose. So bear that in mind. Let's not overcomplicate things. So let's think about a solution workflow. First of all, I'd strongly recommend draw a diagram of the problem you're dealing with and identify the modes of heat transfer that are going on. This is a polite way of saying sit down and think about it. Create that mental model. Understand what's going on before you go any further. Don't blindly go into the mathematics, or don't blindly sit at a computer. After this step, you should expect to know what the answer is, or at least have a very good feel for it. And if, after doing your mathematical and numerical analysis, you get something different, you need to go back to this point and go, why is it different? What have I not understood here? Fundamentally, my mental model was wrong. Why? So, sit down and think about it. Draw a diagram. Figure out if you've got conduction processes dominating. Figure out if you've got convection processes dominating. Figure out if you've got advection or not. Figure out what heat sources you may have on a volumetric basis. So sit down and really think about it. Once you've done that, we need to start to simplify things. Is the problem you're looking at essentially one-dimensional? There are many heat transfer problems that you can make that assumption with. Equally, you may justify that actually no, it's not. This is a multi-dimensional problem, either 2 or 3 dimensions, in which case you've got a more complex problem to solve. But wherever possible, so long as we're still getting an answer that's fit for purpose, simplify the maths as far as you can. Make it the simplest problem possible to get the answer that you need, but don't make it any simpler than that, otherwise you're missing key physics. Once you've decided whether you've got a 1D or a 2D or a 3D problem, then what coordinate system best describes the problem that you're solving? So it's time to think about the geometry. Take geometry into account and then figure out how to simplify the energy equation. Can we put it into Cartesian coordinates? Nice and simple. Do we need spherical polar coordinates? Maybe go into a standard text and make sure you've got every term correct, but also that you're not including any terms that you don't need. Because again, That will simplify how you solve the equation. Finally, think about the boundaries. What boundary conditions have you got? Have you got a specified heat flux? A good example here is an insulation boundary condition where there is no heat flux passing through it. So the temperature gradient is 0. Nice boundary condition to operate with. Have you got a specified temperature instead? T equals Tx, for example. Again, a good boundary condition to work with. For a nice simple problem, for analytical analysis, what we're aiming for is either a first or a second order ordinary differential equation. And if we're doing an analytical solution, that makes it relatively straightforward. You can, with heat transfer, have analytical solutions to multidimensional problems. The mathematics is beyond the scope of what we're going to be talking about, but these are typically separation of variables type problems. We're going to be looking at multidimensional heat transfer, but from a numerical standpoint. But we still need to go through this workflow if we're doing a numerical solution, because we still need to set up the equations. We still need to take the geometry into account and simplify as far as possible to make the numerics easier. And we still need to get the correct boundary conditions, otherwise the problem is meaningless. All right, okay, let's summarize a few key points. One of the things I wanted to get across in this part of Lesson 6 is that heat transfer is actually a really important part of polymer processing, all the more so when you consider the temperature variation of all the rheological properties of the polymers that you're dealing with. The energy equation itself is simply a statement of in minus out equals accumulation, where the quantity that's going in and out and being accumulated is energy. We need to think about energy source terms on a volumetric basis. These can include things such as latent heat release, heats of crystallization, or viscous dissipation. The energy transfer from one part of a material to another occurs by sort of flux-based means, and it can be conduction, it can be convection, it can be radiation, and it can be advection.